Okay, so let's get started. So welcome everybody. Welcome Matt. Thanks for coming and to give this talk. I'm really excited to hear it. I'm Todd Mikowitz. I'm from Microsoft Research. I've followed Matt's work for a while now. I've seen a bunch of his talks recorded, so it's a real pleasure to be here in person and hear his talk. Matt has done a lot of great work in auto differentiation. In fact, I, in my day-to-day job, use the tools that he's built basically daily. So it's really a pleasure to hear him speak on the work he's going to talk about today in JAX. Matt has this innate ability to describe his very complex work. While you're in the talk, you're looking at these very complex slides and thinking, I totally get this. I completely understand what he's talking about. You go home, or at least I go home, I try and work out what the heck he was talking about in that slide. And I'm like, how did I think I understood this? This is so much more complex. But yet he has this ability to, in the moment, explain these ideas that are very complex and make them very easy to understand. So I'm looking forward to that today, Matt, in your talk about JAX. And so with that, I'll let you take it away. Just really quick administratively, we're going to have questions at the end of Matt's talk. You can put them into the chat, and then I'll relay them to Matt after the end of his chat. So thanks a lot.
Great. Thanks, Todd, for the intro. That was far too kind. I'm blushing over here, but I'll try to live up to it. So hopefully everyone is seeing my slides, and I'll proceed, assuming that you guys are. Yeah, right. So we're here to talk about JAX. JAX is the work of many people. This is the JAX team you see smiling before you, and I'm here talking about it, but really all the coolest stuff is from these folks. Great, so let's dive in. So JAX is a system for accelerating machine learning research. So let's start by talking about what machine learning research is. So how would you implement a performant and scalable deep neural network in Python, sort of from scratch? Well, here's how you might start. So you might just try, writing some NumPy code. So this little NumPy snippet, which just has some sort of, matrix multiplies and some tanh nonlinearities, composed in a sequence. This is pretty much a neural network. This is multi-layer perceptron or fully connected neural network. So it's pretty simple to express in just Python and NumPy. And then to go with this neural network prediction function, you might write a loss function which scores how well your neural network is doing at predicting some target outputs given some example inputs. And in this case, our loss function is just sort of a squared error loss. This tells us how good our parameters are at our parameterized neural network is at predicting these outputs. So that's actually a neural network there. That's sort of all there is to it. What is missing from this picture of just Python NumPy bliss? So there are a few things missing. For one, a lot of the deep learning revolution has been powered by accelerator hardware, just like sort of massive machine flops from GPUs and TPUs. And so that is missing from this Python program. How do we get this Python program to run on accelerator hardware? Moreover, if you want to train this neural network, you might want to do gradient-based optimization. You might want to differentiate this loss function as a function of parameters, and then use the gradient to do gradient descent and find the right parameters for minimizing your empirical loss on your training set. We don't have that here. We would like we've expressed the sort of math in this code already. We would like to automatically be able to produce a gradient function and do gradient-based optimization, but autodiff is not in this picture yet. Moreover, really to get maximal use out of this accelerator hardware that we have, we might want to do sort of end-to-end whole program optimization on programs like this, doing things like fusion or optimizing memory layouts, or even deciding to do rematerialization to save some memory when it's profitable. That's also not present in this picture. We can't do end-to-end optimized compilation. You might want to do vectorized batching over examples, more on that in a minute. And finally, you might want to parallelize this kind of computation across many different, not just one hardware accelerator, but many, to do parallelize over big data sets, or more interestingly, with these really big models we've seen recently, to actual parallelism of the model computation itself. So these are sort of missing pieces, and as you might guess, this is what these are the kinds of ingredients that JAX aims to add to this picture. So JAX, first of all, gives us a way to run this kind of a program on hardware accelerators like GPUs and TPUs. We can do that just by changing the NumPy import to import JAX.NumPy, and here I change the symbol to JNP. So now all of our primitive operations, like our matrix multiplies, the JNP dot, or the element-wise nonlinearity, or the sum and the loss function, these are all calling it to JAX NumPy. And by doing that, we're able to execute these operations on a hardware accelerator like a GPU or a TPU sort of behind the scenes. Great. So we have a library for doing NumPy on accelerators. It's pretty cool already, but nothing we haven't seen before. What else do we have? JAX also has automatic differentiation. So we just imported this grad transformation. This is the first example of a function transformation that we're seeing. And this thing takes a Python callable, like this loss function, that evaluates a mathematical function, say f, and it gives you back a new Python callable that evaluates the gradient of that mathematical function. That's automatic differentiation that we can use for training our neural network. Yet another ingredient would be what I've called sort of automatic batching of inputs. So we'll talk about this in a bit more detail later. But for example, if you're doing something like differential privacy training, you want some privacy properties to be preserved by your trained neural network. You might want to compute things like per example gradients, not just the total gradient of your loss function or across all examples, but a gradient for every example separately. So you might be able to add noise or something like this. And with JAX, we can do that efficiently just by using this vmap transformation. If we want to be able to stage out these computations so that we're handing them to an optimizing compiler like XLA, JAX is built on this XLA optimizing compiler. We can do that with a transformation, with this JIT transformation that says stage out these functions so that they can be whole program optimized by XLA. And finally, if we wanted to do some amount of parallelization here, JAX has a transformation for that as well, this pmap transformation that we'll see more of later. And so, as you might see here, we sort of took a NumPy, Python NumPy program that expressed some mathematics, and we did things to it. We did these sort of function transformations, and really that's sort of what JAX is about. The sort of hypothesis driving JAX's design is that numerical computing is about both expressing mathematical functions and then transforming them. And transformations are like automatic differentiation. These are like user-wielded transformations that you can apply to your code. And our sort of the basic idea behind JAX is that NumPy, Python and NumPy solve the problem of expressing computations, expressing mathematical functions pretty well. It's pretty good at doing that. And the real missing piece was being able to transform these functions. And so in a sense, that hopefully will become more and more clear over the course of this talk, JAX is a system, an extensible system for building these composable function transformations by trace specializing functional Python code. So to dig into more detail about what those words mean, let's do a demo. So here's a live demo. Let's see if it works. So this is just a collab. I'm going to go through this quickly, but all this collab material is on the web, and so you can go through it yourself later. Great. So let's dig in. We start with just importing JAX, and JAX NumPy is JNP, and we can generate some large 5,000 by 5,000 float 32 matrix. Great. Then we can do things like NumPy operations on it. Like here we're doing a matrix multiply, printing out the first element of the result, 60, 64, great. So you can just write sort of Python NumPy code. The first hint that something that's not just standard NumPy is going on would be if you sort of looked at the repr. If you call the repr method of this object, this extra object, you can see that it's not a regular ND array, it's a JAX device array. This is just a little hint that indicates the memory backing this array lives on our accelerator device, in this case on our TPU. And actually, values sort of they reside on the accelerator device lazily, and they're only pulled back to the host CPU if we need to do something like print it, like we're doing now, or maybe plot the result or something like this, or use the value for sort of Python control flow if we need to have a Python thread look at the value of an array. But by default, everything computed by JAX NumPy is just sort of a promise, and that means that when we dispatch operations like transposes or dots or even indexing, JAX supports all of NumPy fancy indexing. All these things are sort of executed on the accelerator device, and only the values that are needed are only pulled back to the CPU when they're demanded. Great. So maybe to provide a little more proof that we're actually running this NumPy wrapper on our accelerator hardware, let's import the original NumPy as NP and just do a little race of multiplying these two matrices, so multiplying this matrix by itself, and see how fast it runs. Now, when I run this, I should give a big disclaimer. For some arcane build reason, the NumPy that I'm using here is actually only single-threaded, and so that's why it took like 5 or 6 seconds to do this multiply. If you were running, a nice, MKL-backed NumPy on a high-end CPU, maybe this 5,000 by 5,000 matrix multiply would take more like 200 or 250 milliseconds. So let's think of that as the NumPy number, 200 milliseconds-ish. But you can see that, when we're comparing against JAX NumPy, JNP, this thing is executing much more quickly. It's doing this multiply in 12 milliseconds. It's almost as if, this was a custom ASIC built to do matrix multiplies as quickly as possible. You might also notice that I have this little block until ready on the end here, and that also has to do with the fact that JAX produces values that are sort of promises, and it dispatches computations asynchronously. So the idea is that as we call functions like JNP dot, we'll be enqueuing work onto the accelerator, but we don't necessarily wait for the result. And so to do a timing, until we need it for printing or something like this. And so to do a micro benchmark like this, we just add a little function to say, actually wait until this value is computed, so we know we're timing the right thing. Great, but that's JAX NumPy running on the TPU. Exact same code runs for this entire notebook on the GPU as well in the same way, or on your CPU if you don't have an accelerator yet. But what else does JAX have? So let's get into some function transformations. That's what we came here for. So the first one is automatic differentiation. So we'll import this grad function, which is maybe the most popular function for automatic differentiation. And let's just write a simple Python function. It's got some Python control flow, if x greater than 0. And let's try running it on some random value. And we'll call it on both the value and the negative, so we're sure that we're hitting both sides of this Python control flow. And indeed, if you check, do some of the math by hand, this is indeed grad of our Python callable f. It's giving us back a new Python callable that evaluates the gradient of the function that the original function evaluated. Great, and so because grad is sort of callable in, callable out, we just call it on its own output many times, and this is how you can do higher order differentiation. So here's third or maybe fourth order auto diff, no problem. So that's pretty much all you need to know about grad to be able to start doing some deep learning. So here's our simple, fully connected neural network from that first slide, just the prediction function and the loss. Great. I just wrote some code here to initialize the parameters randomly, and then also set up some completely random data, like a batch of totally fake data, just for illustration purposes. But with that, we can evaluate our loss function on our randomly initialized neural network and our random data set to see how well we are predicting these outputs from these inputs. And we're getting a loss value of 74. Great. We can use grad to do gradient-based optimization. So here's a little gradient descent loop where we'll just iterate 20 times. We'll differentiate our loss function with respect to our parameters, and we will use the gradient to take a small step in the negative gradient direction, and by doing so, hopefully minimize our loss function, or at least make progress on reducing its value. So if you print its value now, it's gone from 74-ish down to 6-ish, and this is training a neural network to predict outputs from inputs. This is the singularity, so watch out. Great, so that's actually most of what you need to know to train a neural network using AutoDiff. There's a ton more AutoDiff content in JAX. AutoDiff is sort of how I got into this line of work to begin with, and so we've had a lot of fun implementing all the kinds of fancy AutoDiff we can think of. I don't have time to go into those things now, but if you're into AutoDiff, check out some of our material online. Cool. Let's look at more. So we got NumPy on accelerators, we got grad, and maybe all kinds of other AutoDiff functionality. Let's talk about end-to-end optimizing compilation using XLA with this JIT transformation. So here is make another big 5,000 by 5,000 totally random input, And this is just some arbitrary function. It's not meant to like represent anything useful. It's just a toy model for illustration purposes. But here's some function, does some element-wise operations on the input, and then maybe it selects a subsection of the results and returns those. So we can apply this function f. There's no end-to-end compilation yet. We can apply it to our input array, and we get some values out. Great. We know that that's executing on an accelerator, but it's sort of executing one primitive operation at a time. By staging this function out to XLA using JIT, we can count on XLA to do a lot of optimizations for us. So we'll make G the JITted version of F. When called G, you might notice that G is the same input-output behavior, maybe up to floating point reordering details, but G and F have the same input-output behavior. So what have we gained by using this JIT decorator? Well, let's do a little benchmark, micro benchmark on just to see how fast F executes versus how fast G executes. And we can see we have a dramatic speed up, 20 to 40x or something like this. And the reason, if you look back at this toy function is, I guess there are two main reasons. One is that these element-wise operations, XLA can fuse these together so that instead of being executed as separate operations with round trips to accelerator memory, it can fuse them together so they're executed sort of in one pass and with fewer temporaries. And then also, maybe that's like 4x of the speed up or something like this. But also just the fact that we're selecting a subset of the results at the end, XLA will use that and optimize the program to sort of do dead code elimination for some of these operations. Great, so JIT lets us stage things out to XLA. Calling it multiple times does not make your code go faster. You can't just apply JIT many times. But I included this line sort of interleaving grad and JIT just to remember to emphasize that these grad and JIT transformations compose arbitrarily. So you can expect to be able to do higher order autodiff with JITted functions, this sort of thing. This example is not doesn't seem that hard, but actually if you have sort of complicated nesting of these decorators with lexical closure and all this sort of thing, as long as your code is functionally pure, JAX will not let you down, and it will faithfully execute the computation that you're describing. So really these things compose. And that's important because you need to be confident that you can use a function like JIT in library code, not just as a top-level construct, but when you're writing libraries. In fact, throughout JAX's internal implementation, we use JIT all over the place for performance. And differentiation and all these other transformations will keep working. Great, so that's one transformation down. I want to talk about vmap next. Vmap stands for vectorized map. It is my favorite transformation, but it's a little tricky to describe and sort of in a way that makes it sound actually interesting. So let's import vmap. Vmap is a map. And so it maps along an array axis, by default the sort of leading axis of its input. And so if we call it on a sequence of integers, 0 up to 8 exclusively, we'll get all their squares if we vmap this squaring function. In fact, it does the exact same thing as if you sort of looped over slices of the array input, applied the function, and then stacked the results together as an array. So given that we seem to have re-implemented vmap in one line, what is interesting about vmap? So the interesting thing is the way in which the computation is carried out. Instead of even though you're expressing this loop at the top level in both of these cases, with vmap it'll take the map you've expressed and it'll essentially plumb this batch dimension through all of your code, through all the primitive operations, and by doing so, it'll be sort of efficiently vectorizing all your operations so you don't have this sort of top-level loop. I guess one way of thinking about it is that it'll turn things that were matrix vector multiplies into matrix matrix multiplies. So this is the reason why we plumb batch dimensions through all of our bulk array code. vmap will do that plumbing for you. To give you a quick example, here is a sort of a blast from the past in the machine learning world. Remember kernel methods? So here is an RBF kernel. The details aren't important, but this is a kind of inner product between two vectors. So we've actually asserted here that we're only being given vector inputs. So like the number of axes, the number of the end in here is 1 in both cases. So this function only applies to vector inputs. And this is how we'll compute this sort of inner product. So imagine you have a function that can be applied to just a pair of vectors, but imagine you have an entire batch of vectors. So in this case, imagine you have vectors of length 3, you have 100 of them batched together in an array. And you want to do something like compute the matrix of all pairwise inner products. This is the sort of thing you do in kernel methods. So we want to get a 100 by 100 matrix where the ij entry is this kernel evaluated at sort of the ith vector against the jth vector in our batch. How can we do this efficiently? Well, we can actually just apply vmap twice to sort of generate this matrix. And if we run, so here we have a gram function for the gram matrix, which is the matrix of inner products. We've applied vmap twice. And then if we apply this with our RBF kernel, which only applies to a single, you remember single vectors, we get the right output shape. That's what I've proven to you here. But again, what's interesting about vmap is how these values are computed. So to be able to show how vmap is doing this computation, we'll use another very simple JAX transformation, which is like a pretty printer, to show you the computation that's going on behind the scenes. So we'll use this make JAXper function to say, how is this, show us the sort of JAX internal representation for how this computation is being executed. So if we run make JAXper here, and the high level point, I haven't described the syntax to you. The high level point is that we're not doing a double loop over the axes of the output of size 100. We've actually just generated a very small program, and this is doing sort of like a big matrix multiply. So by writing a single example code and then combining that with vmap, we're able to generate efficiently batched array level computation to do this computation. So you might think, that sounds cool. If you're used to programming with NumPy or any sort of bulk array library language, you're probably used to plumbing batch dimensions. vmap says you don't have to plumb batch dimensions through your code anymore. But you might think, well, I'm used to plumbing batch dimensions. Is vmap really all that handy? It is handy because not only can you add batch dimensions to your own code, not only can you add batch dimensions to library code. If someone else has JAX library and you want to add another batch dimension to it, vmap can do that for you. But you can apply vmap to code that no human has written. What I mean is you can use vmap together with things like autodiff to express a lot of computation. So for example, to compute per example gradients of our toy neural network example, we just have to vmap the grad of the loss, and this will give us these sort of per example gradients, which come up in applications like differential privacy. These will be sort of like an efficient way to compute these per example gradients. I'm not going to step through the details of this code that was generated, but the high level idea is it's a short program, and we sort of plumbed the batch dimension through efficiently. Great. So that's grad and JIT and grad and vmap. One more transformation for you guys today, at least in this demo. All these computations we've been doing so far have been on one TPU core. So you can think of this as if I were running this demo against a GPU box, if I had 8 GPUs in this computer, so far we've only been using one of them. In fact, if we look at the devices available to JAX, there's 8 TPU cores, or if you think of this as analogous to having 8 GPUs in my machine. How can I program all of them to really make my neural networks fly? So the sort of model that we have for doing that in JAX is this pmap transformation, which, as you might guess from the name, is yet another map. So here we are again squaring these integers. Great, and so pmap acts like map. What's so special about it? Well, one hint you can get that it's doing something different is if you look at the sort of repr of this y object, you'll see that we get a sharded device array out. This is just our little hint to say this array that we're printing is actually backed not just by device memory on one device, it's actually sharded across multiple devices, in this case, 8 different devices. So now we have distributed across our 8 TPU cores, a single integer on each one. And we were just squaring, using the TPU core to square those, which is not a great use of Google resources, but they can't stop me. Let's do something more interesting. In this little snippet, what we're going to do is we're going to generate 8 random pseudo-random number generator keys. We're going to generate 8 keys, and then we're going to pmap a function that generates a random 5,000 by 5,000 matrix. And by pmapping that over all 8 keys, we're going to get a result that logically is a stack of 8 5,000 by 5,000 matrices. But this is distributed across all 8 TPU cores. And then, what can we do with this? We can pmap operations over these arrays. So for example, if we wanted to do 8 5,000 by 5,000 matrix multiplies in parallel, we can just write a pmap this way. And then we've pmapped the mean function, which will take the element-wise mean of each one of those 8 matrices in parallel across all the devices. And then pull, since we're printing, it'll pull that result back and just print it as 8 sequence of 8 numbers. So here are our numbers from doing that. And again, to sort of prove that we're doing something in parallel, you remember before we did a 5,000 by 5,000 matrix multiply. Now we can do 8 5,000 by 5,000 matrix multiplies in parallel, and we're doing it in also about 12 milliseconds as before. So we are actually making use of these 8 TPU accelerator cores that are available to us. So pmap can actually do a bit more than just maps. You may have thought that P stands for parallel. Maybe it does, but maybe it stands for pseudo map, because it turns out that you can express things that aren't just pure maps using collective primitives. Actually, both vmap and pmap, when you you sort of map over an axis, you sort of eliminate it, you can bind it to a name, and then you can use that axis name with collectives that can perform communication, special kinds of communication across that sort of mapped axis. So in this case, as a simple example, we have a collective that's doing a reduced sum over this named axis I. So that's basically going to be a simple function that just normalizes its input. Again, it's doing it in parallel by mapping this over 8 TPU cores, then doing an all reduce to get the sum of all the results, and then dividing it out. So I don't have time to go into the details, but you can actually express pretty interesting computations here by composing pmap with itself. So for example, here we can map over both the rows and columns of our input matrix, bind those axes to names, and then we can express interesting communication by doing reductions across rows of the mapped rows axis, or across the other mapped axis, or do an all reduce across all of these mapped values. And this will be generating the efficient computation that we expect in parallel. So those are toy examples, but you can imagine how this might be useful if you're trying to do gradient-based optimization on all 8 of your GPUs or 8 TPU cores, and you want to use all those cores to make your neural networks faster. So that's pmap, and just to underscore, we can compose pmap with other transformations as well. So here's just a made-up toy example, but showing off some of the lexical closure that I was mentioning before. Here we've got 2 pmaps, so doubly nested pmap, and then we have a grad in the middle. So this is like pmap of grad of pmap, and we can apply this function, and it just works. In fact, we can do a grad on the outside. So this is now grad of pmap of grad of pmap. And if for some reason you want to differentiate through your parallel computation or what have you, you can do that. A slightly less toy example, actually showing composing up even more, is how we can compute Hessians efficiently. So as I mentioned, JAX supports both forward mode and reverse mode. Sort of the fundamental forward mode and reverse mode operations in JAX are JVP for Jacobian vector product and VJP for vector Jacobian product. Those are forward and reverse mode respectively. So we'll import those transformations. Then the fastest way to compute Jacobians that are sort of tall matrices is to use forward mode autodiff, and to use vmap to sort of batch apply a JVP over an entire standard basis of your tangent space. So that's sort of what this jack forward function is doing. We're applying JVP and vmap, so that's 2 transformations. Then similarly, we can for sort of short and fat Jacobian matrices, it's better to use reverse mode. So we can use write a jack rev function that uses VJP together with vmap to do this computation effectively. And then the most efficient way I know to compute general Hessians is a combination of these things, forward mode and reverse mode. And remember, we have the vmap in there. So Hessian is just jack forward of jack rev. And why not apply a JIT while we're at it? That's pretty much how JAX computes Hessians quickly. But if we're doing some kind of neural network research, maybe we have use for something like per example Hessians. So in this case, we've written a function that gets our Hessian of our loss function with respect to our input data. That's the input Hess function. Why not pmap it to get something like per example Hessians, evaluated in parallel across all 8 of my accelerator cores? We get a bunch of numbers out, but you can imagine this is the power of composing up transformations in JAX. So there are more transformations that we've been working on this year. I don't have time to go into them, but maybe be on the lookout for our next demo, our 2021 demo. Just to mention a couple that are interesting, we have another autodiff transformation for exponentially faster, very high order autodiff, which is something I've learned about in the last year or two that I think is pretty fun. So if you ever need to take 30th or 100th order derivatives, JAX has something for you. We also have, maybe I'll just mention this Oryx library, which is quite interesting. So this is not developed by the JAX core team, but it's by one of our colleagues at Google. It's a library for probabilistic programming, and this user made their own transformations for the purposes of probabilistic programming. So for example, the canonical problem of given a function that generates a sample from a distribution, can you give back to me a function that evaluates its log joint density? Because then I can use that in an inference algorithm or something. Oryx contains transformations like that built on the general JAX machinery. So it's pretty interesting that the system can be extended even with more niche or bespoke transformations. So with that, I'll conclude the demo and then spend a few minutes talking to you about how JAX works. I remembered one more thing. So in the spirit of composing up JAX transformations, I helped out a little bit with this research project in Professor David Dubinow's group. The two first authors were Jacob Kelly and Jesse Betancourt, where we wanted to regularize sort of the neural ordinary differential equation models to be fast to solve. And ultimately, from the perspective of computation, this boiled down to needing to use JIT together with vmap to sort of do batching, grad for reverse mode autodiff and training of our neural network, including an ODE integrator operation, and this JET transformation that I mentioned for very high order autodiff. So we composed all of those things together, and that was sort of exactly the thing that we needed for this research project. I linked to this tweet, and I encourage you to check it out because there's actually a very funny GIF that I can't play in this presentation for corporate copyright issues. But check out this tweet. There's a hilarious GIF to go with it. Great. So with that sort of lightning fast whirlwind tour of JAX transformations, let's just talk a little bit about how JAX works under the hood. So JAX is all about transforming and staging out Python functions. Here's a very simple Python function. You might ask, what does this function do? If we want to transform it, we better be able to have an understanding of what Python code does. You might guess that this function adds 2 to its input and returns that as its output value. And maybe it does if you pass in like an int or a float or something. But what if you pass in an instance of this object? This object will SSH into my espresso machine and have a side effect that brews espressos in my kitchen. And it's a beautiful thing about Python that this one tiny function f that we've written can be reused. Like, what great polymorphism we have here that we can drop in any object and overload the plus operator. But as you might imagine, this is difficult for if we're trying to build a sort of compiler or a transformation system. The fact that Python code could be so dynamic and so polymorphic, it's hard to predict what it's going to do before you actually run it. And so this might be a problem if we're trying to stage out Python functions or transform them. So what can we do? One thing you could imagine doing is trying to constrain the behavior of this Python code by adding type annotations, so the source text. So for example, you could imagine saying, well, I'm going to promise you that this input is always a float 32, and then, okay, we can reason about what kinds of behavior this Python code might have. JAX does not take that approach, so that's quite a sensible one for languages that want to constrain behaviors. Instead, what JAX does is it sort of takes advantage of the extreme overloading and polymorphism of Python and uses that to implement a very simple trace-based specialization mechanism. So instead, we sort of just in time ask a question of this function like, I don't need to know what it can do for all possible inputs, but what would it do to a particular set of possible inputs? And then if we can ask and answer that question, we can get a view of this Python code specialized just to a particular set of possible inputs, and then we can work with that. So let me just walk through a little bit operationally about how that works. Here is a implementation of the log base2 function. This is pretty much an implementation in our JAX NumPy library. You'll notice we wrote it in terms of these lax operations. So lax it's an anagram for XLA. It's just that is our library of primitives. So like programs bottom out as compositions of these primitive operations, and these are our primitives, these functions in lax. So every transformation knows how to deal with these primitives. We have a table of rules for each primitive. Great. How do we deal with compositions of primitives? So imagine that a user has an array in hand, and they want to JIT this log2 function, and then apply the result to x. So what we do is we wait JIT doesn't do any work until you try to apply it to an input. Then we have this input x. And what we do is we say, okay, we have the Python, the sort of opaque Python callable. We don't look at Python source text at all, but we have this callable object in our hands, and we have this example input. And then what we do is we trace this Python callable by replacing its input with a sort of dummy object, with a tracer. And we replace it with an object that represents a set of possible inputs. So it's sort of an abstract value. It's a tracer with an abstract value. And so in this case, we might be replacing this input. The user asks to evaluate this function on a particular concrete input, but we're going to replace it with a value that represents a set of all possible arrays with float 32 element type and shape 2 by 2. So we just call the regular Python function using the regular Python interpreter on our sort of dummy object, and then we record all the primitive operations that are applied to it to produce the output. So in this case, every time we hit a primitive operation, we're sort of building our IR, that we call a JAXper IR, for like JAX expression, representing this function. And so this is just a sequence of simple primitive operations applied to the input to produce the output. So an important caveat that I want to underscore is that JAX only works on pure functions, so Python code that is functionally pure. And this is a major reason for it. It's that our tracing mechanism works fine, recording the operations that are applied to the input to produce the output, if we're tracing a pure function where the output is determined by the input and there are no side effects. So apparently I've learned that Python actually does allow side effects. And if a user writes, a sort of global side effect in their code, we will not be getting a faithful representation of this Python code specialized to our set of inputs because we sort of just don't see the side effect in our simple tracing mechanism. And so we just require the user's promise that the code that they want to transform with JAX is functionally pure. There, respects referential transparency, and there's no side effects in it. But if we have pure functions, we can use this kind of tracing mechanism to specialize out our JAXper, and that JAXper represents what this Python function would do to any input from our set of possible inputs that we traced it on. So just to say that we don't, when we do tracing, I mentioned that we might ask this question of how does this code, how does this Python code work if we give it any possible array of this particular shape or D type? So we do specialize the Python code on some amount of information. We say the input's an array, and this is its shape. At least for JIT, we say this is its shape and this is its D type. That means that we can specialize code like this that has a Python switch on what the rank of its input is. And in this case, we will just get different specializations, and JIT will sort of retrace specialize when it sees a set of inputs with set of shapes and D types that it hasn't seen before. So we'll just get different specializations of this Python code. However, if using JIT you have code like this, which switches on the value of x, we don't have that available at trace time. The whole idea of JIT is to delay the computation and stage it out. So we're not executing the computation operation by operation on the particular values. We're just tracing on abstract values that representing the sort of shape and D type of these values. And so if you write code like this and then try to use JIT to stage it out, you'll get an error. If you've ever used JAX, maybe you've seen one of these. JAX will never sort of do the wrong thing behind the scenes, but it will complain loudly about not being able to trace this code, at least with JIT. However, you may have noticed that this is the same function that we saw in the demo, and we saw that we were able to differentiate it. So we were able to use the grad transformation on this code. And so clearly something is going on to be able to support this. Python control flow, value-based control flow with grad. And in fact, in general, the way we like to think about it is that different transformations naturally specialize different amounts. I don't have time to go into the details, but this means that different functions, there's different sort of scopes of what kinds of functions can be trace specialized for different transformations. So that was all step one about how we trace specialize Python code into a JAXper. Luckily, it's only a two-step process. Let me tell you about step two. Now that we have traced this Python function, how do we actually transform it? So we think of a transformation as a reinterpretation, or as sort of an interpretation of this JAXper. And so for every primitive, we have a rule. So for our forward mode autodiff, this is what the rules look like. For every primitive application, we have a rule for how a JVP transformation operates on it. And then we just write a little interpreter that walks the JAXPer and applies these rules. And that's how we get sort of a JVP of a composition of operations. We just walk this JAXPer with a simple interpreter. This is slightly specialized, but this is essentially how simple JAXPer interpreters look. Now, what's really special is this JAXPer interpreter is itself a Python function. And so if you want to do something like higher order autodiff, it turns out that you can actually just trace this Python function itself. You can trace the interpreter. And so you can replace the inputs with tracer objects, trace its operations, and then repeat the process so that you can transform further. So this is really the secret to JAX and how we get composable transformations. It's that the interpreters we write in Python are themselves JAX transformable. So if you like, here's a simple lifecycle view of how JAX transformations look. We sort of have Python functions, we trace specialize them into our JAXPer IR, and then we write an interpreter for that transformation that interprets this JAXPer IR. But because that interpreter is itself a Python function, we can then repeat this process and apply more transformations. If you like, ultimately, when we have a stack of interpreters, we need to sort of bottom out somehow and compute values. And you can think of the eval interpreter or maybe a compilation interpreter as special interpreters that sit at the bottom of the stack. Now, there is actually this detail that I mentioned where to be able to handle things like Python control flow in grad, there's actually a sort of detail to how JAX works where we can actually fuse the sort of arcs in the cycle together where we can transform as we trace. And as a result, this helps us handle things like Python control flow and also makes sort of debugging experiences nicer. I haven't talked about that, but I just wanted to mention that there's this short circuit. So in the last, I just have a couple more slides. Just thought I'd overview what we've learned. So this is sort of something of a research system. What have we learned by having users make use of JAX? So we've gotten a lot of positive feedback about how JAX is easy to use. I think the primary motivator for that is the separation between people writing Python and NumPy, which they're pretty familiar with, to express programs. And then on top of that, JAX's API is basically just these transformations. And we like to say that each transformation essentially just has one function and no data structures that you need to learn about. So the API is pretty simple. People like that JAX has good out-of-the-box performance. People really make use of all these transformations. And I think also maybe the biggest, most interesting thing that we've learned is that functional programming works really well in this domain. So actually, we were met with some skepticism when sort of initially developing JAX, where people suspected that maybe programmers don't want to learn functional programming. But it turns out that in this domain, the things that we want to express are so well aligned with math that programmers don't like to think in terms of buffer, reference semantics and updating things in place and stuff. They would much rather just model the mathematics directly and then have an optimizing compiler that handles low-level details about how things are computed. It means that the research that people do in JAX is more reproducible, easier to debug, and really this is what keeps our implementation very small and simple as well. Is this assumption that user code is all functional. There are, however, some big limitations, and I, to do justice, would have to spend a lot longer on each one of these bullets. But I just thought I'd mention one big limitation is that JAX is accepting for expressing programs. It's really more or less accepting the sort of NumPy bulk array programming model. I say NumPy, but MATLAB, TensorFlow, PyTorch, maybe APL, like all sort of fit in this scope of a sort of bulk array programming model. And JAX doesn't really change that. And for the same reason that NumPy had to grow escape hatches for programs that didn't fit well into that model, and you can always escape into the sort of meta programming goo of Python, but at a big performance penalty. You can imagine similar things for JAX where you might need an escape hatch where your program doesn't fit into the bulk array programming model for some reason, and you need to get out of it. That said, deep learning is maybe the perfect domain for the bulk array programming model, so that's fortunate for us. Maybe I'll also just mention that the last point here is that it's a limitation that our transformations only work on pure functions. On the previous slide, I said that was a win or like an advantage, but it's also a disadvantage, especially in that this idea that user functions have to be functionally pure. We don't have a way to check that. If users write functions that are not pure, they just end up with crazy tracer errors happening. Eventually, they can be sort of arbitrarily bad. So it's quite a I think quite an Achilles heel that we're relying on users to write functionally pure code, but we have no way of checking that contract. Finally, I'll just mention JAX was used in MLPerf this year with some really exciting results. Google did really well in the sort of like make these things run as fast as you can on whatever hardware you have category. JAX actually has had the fastest ResNet 50 ImageNet training time, and the transformer machine translation task training time, where we were using 4096 TPU devices and training in what used to take weeks in just 16 seconds. So that was exciting, sort of projecting JAX at that scale. And finally, what the most exciting thing to me about JAX is all the stuff that's getting built with it. Like things that even go beyond traditional deep learning, where people are just really getting creative and applying it in a lot of domains. Okay, so that's it for the slides and the talk. Thanks for your attention, and I guess now we can do Q&A.
Awesome, thank you. Nice. I'm going to clap for you, and
right.
Given that you're not going to hear other people clapping.
I'll believe that they're clapping. They're in their own.
Okay, yeah, they're there. They're there. I can see them. You can't, as the moderator.
All right.
Great talk. Awesome. I loved it. I've been a fan of JAX for a long time. So I don't have any questions here in the chat. Please, audience members, type them in, and I'll relay them here if you have them. While everybody starts thinking of their questions, I'll maybe prime the pump here and ask a little bit about just debuggability. So I'm curious, right? You have this very nice system that composes across all of these different operators. You've got a compiler in the backend in XLA that's taking advantage of floating point non-associativity to produce, for instance, gradients that may not necessarily be the same after a transformation. You've got pmap and vmap that might be applied. You've got parallelism through an all-reduce across machines. Something goes wrong. What's your story there? How do you dig into this and understand who to blame? And yeah, I'm just curious if I know you've given thoughts to it, but I'm curious if you can elaborate on what you've done here.
Yeah, yeah, debuggability. I think there's a lot of different angles for how to come at that, and there are a lot of levels to the system. I think for JAX itself, it's sort of very much like the usual Python story of I think people often jump into debuggers, and they rely on runtime error messages. So we try to make those informative. We have source provenance tracking. Actually, we sort of added recently, and we're trying to plumb those through to error messages so that people know. First of all, when you're transforming, the fact that it often transforms as it traces, you can often get an error that's in a stack trace while it's executing your code. Maybe you'll have a ton of JAX frames on top of that, but that sort of helps. You can sort of enter a debugger in your code and maybe inspect some things that JAX is doing. For error messages, we also try to plumb source provenance, given the information that we're tracking. But I think ultimately, yeah, it comes down to debugging Python, like having a sort of interactive debugger. That's quite different from maybe how you might imagine debugging systems with a static type system. And those are sort of two different schools of thought. We do make the interactive debugging worse because we're adding all this, we're adding extra layers of information, like we're boxing your inputs up in tracers and sort of thing. Right. So I think it's tough. I think it's we do what we can to make it as approachable as possible, but it is tough. Then there's the aspect of debugging parts that aren't JAX proper. So like when we stage out code with XLA, how do you know if you're hitting a compiler bug, or how do you do performance debugging? So there are feedback tools for that sort of thing, profiling, and we could do a better job documenting them. But luckily for us, XLA powers really important accelerators at Google, so there's really good performance profiling stuff. So like that MLPerf work that I mentioned, a lot of that was digging into detailed profiles and looking at things there. So I think researchers inside Google certainly make use of those things, and if we documented them better, probably external folks would as well. But yeah, it's I think a pretty if you were looking for things to dramatically improve upon, if you're like, what if we built a completely new language and we weren't just trying to embed a numerical language in Python, do this, that might be one of the axes along which you could improve dramatically would be something like debuggability.
Cool. Okay, so we have a question here from Artem. So he says, what's the gradient, or she, I don't know, what's the gradient of the following function, def sample? So if x is 0, return negative x, else return x. So I think this is...
This is a great question, and I'm so glad it was asked, almost as if I planted it. So it returns the wrong answer. Actually, I need to read the question, but like it'll return -1 or whatever the wrong answer is. So assuming that it's at 0. So this is actually, maybe this is an old example, but it was first brought to our attention by my colleagues and manager Martina Body and Gordon Plotkin. It's quite interesting about so just to sort of set the stage, this example is a denotation of the identity function. So there's no mathematical differentiation pathologies. It's if x is 0, return -x, otherwise return x. That's the function. So it's infinitely differentiable and all this stuff. But it is written as a bit funny as a function, as a program. And if you differentiate this and evaluate the derivative, the gradient or whatever at 0, a lot of systems will give you the wrong, including JAX, will give you the wrong answer. They'll say -1 if you evaluate it at 0. And it's because ultimately, if you sort of walk through the tracing, let me share my screen again. If you walk through the tracing process that I described, a great slide on this that I couldn't find, sorry. If you walk through the tracing process, you'll sort of accidentally specialize on x being equal to 0, and then you'll see this -x branch. But in fact, the derivative of this function should be 1. So you'll sort of like take the wrong branch on the if. So actually, we do have a way of thinking about this. We built JAX to be able to at least produce an error in this case, and then we sort of never implemented it. So, but I'll describe to you, there's a line in the to-do where it's, why we set up this abstract hierarchy the way we did was to be able to solve this error. So what's going wrong here? One way to think about it is that when we specialize this Python function, to be able to differentiate something, we can't specialize all the way down to a point, in this case 0. We need to specialize down to like a neighborhood, right? Like when we're asking, how do we linearize this function, we need to know how it behaves within a very small epsilon ball neighborhood of the point at which we're specializing. But we can't specialize all the way down to a point. And this example is sort of exploiting that. If you want to look at it, I guess like topologically or something, the if x equals 0, this thing is not a smooth function in this, from the real topology to the discrete topology, because the pre-image of 0, if you like, is not an open set. Anyway, of this like Boolean. So if you like, there's something that's going wrong with specializing this function all the way down to a point. So if you look in this slide, the reason JAX is getting this wrong now is because out of laziness, when we trace specialize for autodiff, we are actually trace specializing on a concrete value, which is like specializing all the way down to a point. And so we don't detect that like if x equals 0, we shouldn't be able to decide what that is. So we specialize on the to the point 0, we'll say, oh, x equals 0, that's true. But if instead we specialize like the way we say that we should in slides, if we specialize down to an epsilon ball, then we can actually say x equals 0. That could be, instead of saying that's definitely true, we would say, actually, I need to produce an abstract value which represents the set true or false. And then Python would raise an error there, that same abstraction error. So we sort of designed the system to be able to do that by saying we can just have an epsilon ball sort of level in our abstract hierarchy, and then we'd be able to take control branches like if x greater than 0, or x not equal to 0, or x equals 0, so long as the sort of epsilon ball that we have is definitely separated away from 0. But if we were specializing on the point 0, we could raise an error. Anyway, this is maybe a long-winded way of saying that the JAX system is designed to be able to raise an error in this case, but we never implemented it, in part because it's sort of, I don't know, from a practical point of view, it's something of an academic pathology, I think. But it is a very interesting one. So I mentioned Martina Body and Gordon Plotkin have a paper on this where I'm not a PL expert, by the way. My training's in machine learning, so I'm probably going to say something wrong here. But they have a paper where they were asking the question, how could you build a language where it's impossible to express functions like this, where somehow we can rule out this kind of like pathology, which again is not a mathematical differentiation one, but it's like an autodiff one about how the program is written. And they sort of came up with a language where all sort of computations are always smooth, including this one that's involved in the predicate. So I think I couldn't really understand their paper, but I think what they're doing is building a language where this is ruled out by construction. But indeed, you can write this thing in Python, and JAX will tell you the wrong answer, which is -1 at 0. I have, if I find a slide or something, send me an email if you want to see more slides on this question. But it's a good one. So thanks for asking it.
Great. Okay, any more questions, folks? I don't see anything coming in, so I have some more. So yeah, can you maybe touch a little bit on what, yes, okay, so Artem says, yes, I read the Gordon Plotkin paper. Good. So
Cool.
we had a handful of things around debuggability, and you mentioned that there's, that's where somebody could jump in if they wanted to, as an external person, maybe help or think about, right? So JAX is open source, right? Or some components of it are. What do you feel like you could offer up to the people that are in the audience about, what could they provide JAX? What do you see the external community, something that they could potentially, how would they help you?
Yeah, yeah. Thanks for the question. It's very positive community building sort of stuff. Indeed, all of JAX is completely open source and developed in the open, all on GitHub. In fact, most of the team members, myself included, never really learned how to use our internal like Google infrastructure for like version control and stuff. So we have to use GitHub. Yeah, it's all developed in the open. In terms of how people can jump in, actually just this morning we got one of our best contributions ever, which was someone added support for Windows, basically improved our build process so that JAX can run on Windows, and I think almost all tests pass. Which is really promising.
Cool.
So that's, wow, thank you to that open source contributor who did that. Yeah, I mean, we're, on GitHub, we mark sort of issues as like good first issues. It is a bit of a challenge to dive into the JAX system because it is, a fairly, intricate mechanism, and, some parts of it are challenging to develop. That said, things like, error messages can always be improved, or even just bug reports are actually a big help to us because we're very feedback driven in terms of what we work on. And so even just folks letting us know when things break is a big help. I think the best contributions that people have made so far is just building things on top of JAX. So there was a bullet that I didn't have time to talk about higher level libraries. There's people out there, Googlers, but also non-Googlers, who are building things on top of JAX, and I think that's really a great way to get involved in the community, which is just like build cool things with it. We've seen people physicists at national labs start building it and using Autodiff for their through their simulations, this sort of thing. In fact, some of our interesting features have come out of even just GitHub issues where people have noticed a problem or said like, hey, can JAX help me with this problem that I have, this applied problem? And we've ended up developing sort of new JAX features, or thinking about JAX in a different perspective based on those things. So yeah, please come to our issue tracker if you want to help out. There's a bunch of small issues marked good first issue, but we just love hearing from folks, and especially if you're doing something that's like pushing the limits.
Cool. Okay, so we have two more questions here that have come through. So the first one is follow-up from Artem. So if the user doesn't adhere to a purely functional contract, the tracing will fail. Is it possible that it will not fail and the user will get garbage out? And I think there was kind of a somewhat similar comment too. Someone was asking, is it possible to basically have a slow mode where JAX can dynamically catch the types of problems that can't be properly auto-diffed? So I think somewhat maybe combining the answers or combining the questions together, is there a way to kind of find a slow mode or some sort of a debugging step where you could potentially throw higher amounts of information at the user in both these situations?
Yeah, those are such great questions. The short answer to is it possible to get garbage out for some, like it's definitely possible that an error won't be detected. I don't have an example in mind where you would get garbage out, but I believe that you could definitely construct such examples. So yeah, it's real potential issue, and I'm like pleasantly surprised that I think functional programming works so well in the domain that that's the only reason why we're not bit by this sort of constantly. But yeah, so for example, if I gave the example in the slides where we like if the user has a function that appends to a list or something like this, appends a value to a list, our trace version of that function won't have that side effect. So that's a kind of garbage where we're not faithfully reproducing the Python function. But also will probably be, the Python object that you're appending to that global list will probably be one of our tracer objects. And so then that tracer is just like sitting there. It's one of our objects. If you operate on it later, that's when you get a weird error message. So the error won't be caught immediately. And I think probably, I think actually one of my colleagues made a scenario where in Python you can do things like, here's an example where I guess you get a sense of garbage. You can mutate closures. Like you can't mutate closures directly, but you can close over mutable values. You can close over a list, right? And then you can have Python code that has a function. Maybe you JIT that function, but it closes over a list, and then you mutate the list. JAX, the soundness of its compilation caching relies on you not doing that. The functional assumption's built in there as well. And so if you call that function that had its closure mutated, we will not have staged out the updated results. So we'll just call the old function again, and so that'll be sort of like garbage. You can get numerically an answer that would be different between if you had a JIT on that function or not.
Right.
So yeah, you can definitely get garbage, and I don't think it's even we've brainstormed some clever mechanisms to try to cache some classes of these errors, but yet there's so many more possible mischievous ways you can violate functional purity in Python. I doubt we'll ever be able to catch all of them without writing our own Python implementation or something. Even then, it might be tricky. So yeah, it is possible to get garbage out, and I think one thing we benefit from is functional programming has this mystique. Like I think people are like, wow, the wise folks do functional programming, and so people feel unclean when they're doing like global side effects and stuff. And so I think we benefit from that, where if users do that, they sort of feel bad about it. And if we tell them like, oh yeah, JAX did the wrong thing because you had a side effect, they're willing to take the blame themselves and be like, oh, I have sinned and committed a side effect. It isn't JAX's fault. But yeah, JAX can sort of fail arbitrarily badly, I think.
Yep. It sounds like there's a little bit of the discussion is a little bit about you get a benefit from being staged and taking on all of the warts of Python, but you get the benefits of Python as well, as opposed to, for instance, starting from scratch and writing your own language, right? Where you can basically, as you said with the Gordon Plotkin paper, right? You can rule out certain types of behaviors by construction, but there's a trade-off there, right? Because then you're building up a language from scratch, right? And so.
Yeah, that's right. And Python has a big community. Also, if you were to design a language that was going to be good for this programming model and potentially for staging and transformations, Python's really good at that. And so I think to do something different, you'd have to do much better on some axis. I don't think having an existing, I think there are challenges to saying retrofitting an existing language to try to do some of these things if ultimately it's going to be the same programming model, or for some reason, it's not able to just catch all the errors. It's just able to catch a different set of errors. So, right. So some of my, a few of my colleagues on the JAX team are working on this project called DEX, which is an experimental language. If you Google dex-lang, maybe you go to github.com/google-research/dex-lang, and it's sort of very, very new, but it's trying to embrace some of these ideas where we want to have static type checking. Forget about all this complicated tracer mechanism and all the weird errors and the user promises and stuff. Build this language well, but also try to do things that JAX can't do, like having going beyond the bulk array programming model, or having certain kind of type of side effects that are represented in the type system. There's all kinds of interesting stuff going on there, but yeah, it's hard to stand up a new language.
Yeah. Okay, so I have a kind of an ambiguous or a naive question. I'll put it that way. So with vmap, suppose that I have something where I want to understand the semantics of the actual batch index. So I want my program to do something smart, like maybe like some sort of a normalization in terms of that index. Is that something that's expressible with vmap? Or and this is really a lead question because I'm curious, and I don't know it might be trivially true, but the question I really have is there ambiguity when you take a program? Could I have some complex tensor expression where it's ambiguous which axis you actually are trying to, which axis I'm actually intending the computation to flesh through this implied index?
Yeah, I guess there's yeah, I think I understand your question. And the short answer is no by design, but only because of how sort of vmap works. So I think something that vmap is not, but that is hard, is if you took bulk array code and you tried to automatically parallelize it, like you said, here's a bulk array function, it's got the inputs have 3 axes or whatever, and I want to parallelize along this axis.
Yep.
Do that. And I think it then can become ambiguous about along which axes the intermediates might be sharded or something like this. And this is something that array-oriented compilers can try to do. XLA is actually extremely good at doing this kind of thing. So XLA works in terms of the bulk array program model, and you can say shard this across. And I think this work at other companies and academic labs as well that do it. And that's sort of a hard compiler problem. vmap does not solve a hard problem, and that's why I say no. It's actually doing something very simple and easy behind the scenes. So if you remember in that example that I showed where I wrote the RBF kernel, and then I asserted that it's only being given vectors.
Yeah.
When we vmapped it, somehow behind the scenes, there have to be bigger arrays, like batched things, like 2D arrays going on, and yet we were able to apply this function. So the way to think about vmap is that it is like a map would. It's like the code that it's mapping doesn't know about this mapped axis somehow. It's like it thinks it's only operating in 1D. As long as our rules are sound, the sort of mapped axis is hidden behind the scenes, and then we're doing the bookkeeping to say like, actually I'm holding on, so a vmap tracer object, for example, has a 2D array behind the scenes, even though it's presenting itself as a 1D array. And then we're saying like, oh yeah, and this is the batch axis. And then we, again, as long as our rules are above 3, and we do have hundreds of thousands of tests of them, something can't go wrong. And again, it comes down to decomposing the, you see complex expression. Complex expression is just a composition of our primitives, and our primitives don't get too complicated. Maybe 1 or 2 of them, the batching rules were real head scratchers to work out. But for most of them, it's pretty easy to carry along a batch axis. So we were doing batch axis plumbing once and for all, but it was like the kind of things that programmers do all the time. So anyway, I think with the vmap and pmap programming models, because they're forcing the user to write these sort of maps explicitly, and they sort of the mapped axis is not even present, you can't screw anything up with it. You mentioned also some kind of normalization or something, which I interpreted as like a mention of things like batch norm. So
right. But now it makes sense in your answer though, right? Because you would do it on the result. You have access to the thing that has been vmapped over. So presumably the result of that.
Right. So you can either vmap sections and then like have the sort of axis appear positionally. But also that's where, so I mentioned I didn't show with vmap, but actually both with vmap and pmap, you can associate a name with the mapped axis. And these things have to be sort of like globally unique. Actually, maybe they can shadow each other. But let's imagine you get globally unique names. Then you can operate along that batch axis, but only in a very particular way. So for example, you can do an all reduced sum, and that's enough to do batch norm. But you can also sort of do other collectives. It's kind of like a NPI like programming model. So you can sort of operate along that batch dimension, but in a very controlled, prescribed way that is sort of set up to prevent mistakes. It actually is. It's interesting because it rules out. It is like working with named axes, and so it rules out certain kinds of shape errors or like transposition errors when you're operating along these named axes.
Interesting. Okay, so anybody else have any follow-on questions here? I think with that, Matt, I think It was great chatting with you. Thanks for taking the time out of your day to explain JAX to everybody. I really appreciate it. I had a great time. So I think with that, we can probably close out the session here.
Likewise. All right. Thanks,
All right.
Todd. Thanks, everyone.
Yep. See ya.
Thank you.
Thank you. Bye-bye.
Thank you.